Hey, yeah, thanks for the introduction. Can people hear me? Is it okay? Okay. Well, I think it's expected that we have a diverse audience because this is a diverse conference. But I was just told by our previous speaker that, for example, I think he did a poll and he said, "How many people are doing computer graphics? Only two of you." Um, but his talk was mostly about robotics, and my talk is actually more about computer vision rather than computer graphics in the sense that how can we, graphics is about modeling the world, right? So how can we capture the inductive biases about physical world so that you can render beautiful things? And so we're going to talk about if you have knowledge in computer graphics, if you can actually model things really well, then how does it help you to solve perception, right? So to reason about and understand what's going on in the world. So it's like a vision problem. So, but before I start, I think I can do the same poll as suggested by Yuan. That is, how many of you have a background or do research in computer vision? There are four. It's better. It's doubled. How many of you do like robotics? No. And what about computer graphics? I know there's a few over there. Okay, so most of you, I guess, you have a background in math or something, right? You study math. Okay, great. Thanks. Okay, so then it will be easy because I think I've learned that and when you give a talk in computer vision, people say, okay, it's like it would be more popular if you have fewer equations. And nowadays it's all neural networks, so it's actually hard to have equations. So we don't have like one or two equations. So I assume if you have background in math, it will be like easy for you. Everything should be very easy to understand. Okay, let's get started. So we're going to talk about how we can, modeling. So we live in the world and we see like all these objects and peoples, and you want to reason about, oh, what is the object, right? What's the geometry? If you want to navigate like from this place to the door over there, then you realize there are all these chairs and people, and you want to avoid obstacles so you don't have collisions. So you have to understand the geometry and of course the semantics. What's the category of the object? But also, more fundamentally, I would say the physics of the object. What's their geometry? What's their materials? What's their textures? So they can think about, what is the objects and how what will happen if you move around and how would it look like, as well as if you want to interact with them, then what will happen, right? If you have a cup, you realize, okay, it's kind of soft, it's made of paper, so you want to when you want to interact with it, you have to not put too much force, and if there's coffee inside, you don't have it spill over. So all these factors are important in what we call understanding the visual world. And our goal is is that possible for us to leverage knowledge from computer graphics, from physical object scene modeling, by understanding what really belongs to the objects. That's what we call object intrinsics, like their geometry, physics, textures, materials, to help us to solve this perception and understanding problem. Okay, so here's the example, right? You have a view and the object, in this case it's a lion, and you realize there's a lion, that's its semantics. But you also understand that there's this underlying physical object intrinsics, like what's the geometry of the lion, what's the material of the lion, how does it look like, and its possible motions and stuff like that, right? So the process of computer graphics, or at least the subject rendering, is okay. You take all these representations. We have beautiful CAD models, beautiful meshes of the lion, and you have their shaders and everything, and you can render and produce the pictures of the lion. Okay, so a lot of the problems we care about in vision is, okay, is that possible for me to invert the process, right? So that I can de-render the picture. I can take the image of a picture, I can take an image of an object like a lion, and I want to infer, what's the material, what's the shape, what's the motion, possible motion of the object. And ideally, there's always like uncertainty, right? So you can't really have full knowledge about what is there. So there's an underlying possible distribution of line of the shape and materials and things you care about, and you want to model that distribution as well. So how can we do that? Right. So computer vision, or nowadays more so about graphics, is has a lot of connection nowadays with all these data-driven machine learning methods, and you want to use AI to solve that problem. But if you want to use machine learning, and of course you need data, right? So the classical success in computer vision is ImageNet, where you have all these. What happened there is you have 1 million or 10 million images, and then you have the input as an image, but you also annotate. You have the supervision of what is there in the image. Is it a cat or a dog or a person? So you annotate all this data, and then you train a large neural network, and it was very successful in classifying what's the semantic category of the object in the image. Okay, so if we want to replicate that success in the tasks we care about, like reconstructing shape, materials, and motion of the object, what will happen, right? So how can we do that? And the straightforward idea is, okay, what if I just collect the labels, right? So can I just, instead of labeling what is there a cat or a dog or lion in the image, instead I label the things I care about, such as the geometry, the possible motions, the materials, and all these things, right? So some people have been trying to, of course, these data are really hard to collect, but you can see that there has been some attempts to collect such kind of data, especially in the kind of a mocap labs, motion capture labs and stuff like that, right? That's how, you see all these like special effects, or in computer games, right? All your characters or movies, when they're behaving and doing all these different things, a lot of these are like data motion captured in labs. The issue is, it's obvious that compared with the large amount of data in the internet, right, which you can use, or even the relatively smaller amount, but still a large amount of data like ImageNet, where you can label and you can just label what's the object category in the image. Now you want a lot more data, and these data are really hard to capture. It's hard to capture the geometry, and not to say like what's the shader reflectance of the objects. It's really hard, expensive, and tedious to capture those data. It's infeasible to scale up to the real world, and also fundamentally, it's also not capturing the causal structures behind it, right? So you can't really reason about, oh, what if I, see an object from a different, okay, that you can probably do. What if I change, let's say, our particular underlying factors about the materials of the objects, then what will happen, right? So you're not really capturing these kind of causal structures. So the data-driven list, let's try to think about where the data is, right? So you can see that, okay, there are a lot of data from the internet. You can try to learn in the wild, in the sense that it has all these videos about, discoveries about all these cats and animals moving. And is it possible for us to just use those data, right? So they're very rich, they're in the wild, they're free. The issue with that is, you don't have labels, right? So you can't do supervised learning anymore. So if you can, when you can do supervised learning, you're like, okay, take an image and directly predict what's the shape. Here you have a lot of data of objects moving, which of course, it contains information about how the lines will move and the shape and stuff like that, but you don't have annotation, right? You cannot do supervised learning anymore. And the natural idea is, okay, is that possible for us to put, but these data are not, they're not like unorganized, right? They're organized in a particular way. And the way they are being organized is the subject that people, an entire field has been studying for decades. That is computer graphics and rendering, right? So you have all these models about object geometry and texture. You have all these fancy equations trying to approximate what's light transport and how the object reflects light and stuff like that. So is it possible for us to put this forward model into the loop in our inversion process? So that's how we're, there's a classic idea in computer vision called analysis by synthesis. There's this modernized version where you can do everything with neural networks. And even that is kind of a bit outdated, but I still can say it's kind of a modernized version. You have a lot of raw input, and you have a neural network that's trying to de-render the whole thing into things you care about, like shapes and materials. And because you don't have supervision here in the middle, right? You don't know what's the shape or material of the line in the video, but you can re-render, using the knowledge in computer graphics to re-render all these inferred properties into the original input image, and you can use like a reconstruction loss, right? You can solve this, and since all you care about is analysis, but then you can solve it by doing synthesis, right? To render and try to explain the input. And on top of that, sometimes you actually have a little bit of knowledge about the things you care about, like you may have some priors about the shape or materials and stuff like that. So you can actually maybe leverage these inductive biases into the modeling of the process. So I think here inductive biases means two things. Right? One is, the rendering structure itself, right? For example, how light will interact with the objects given its geometry and material is a level of inductive bias. A second level of inductive bias is on top of that, maybe you have some specific knowledge about, okay, maybe the object is homogeneous, or you have some particular parameterization of the materials that it will work very well, so you can leverage that as an inductive bias as well. Okay. So the whole process will be like, you can train on a bunch of in-the-wild videos, and during inference, during testing, often you only need is a single image, right? You can take a single image, and then you can just de-render into the things you care about. So I'll give some examples about how we realize this, as well as some more recent developments in the sense that we sort of, expanded the framework, or even kind of, we can say, changed it in a pretty substantial way. But before that, the first few examples, it would just be like, under this kind of big analysis by synthesis framework, how we have realized and built a few systems that can do pretty amazing things, especially doing inference, doing testing. That you just need a single image that can infer a lot of things that you care about. Okay, so we start in the case with a single object, which is and single static scenes, so which means we don't care about motion, And also, we don't care too much about the form or the hierarchical structures of stuff. We just assume there's a single object, homogeneous, and let's see how much we can get from the test image if you can train a bunch of inner-while data in a self-supervised way by leveraging priors from computer graphics. Okay. So I'll say, and as I said, object intrinsics is something they bring various inductive bias. Maybe you want to leverage. So for example, if I show you a picture of this vase, then you realize, there is a bunch of underlying object intrinsics like the surface normal, which is the geometry, but also the albedo, that is how it reflects light, and the materials of objects. Albedo, the texture, it's like the true color, the texture of the objects, and the material, which is, think about it, how it reflects the light, right, to make this vase look like a vase. It's kind of shiny. And also, some of the lighting components like diffuse specular maps and environment. And if you look at more closely at them, especially for this vase example, realize there's a bit more inductive bias that you can leverage. Right? One is for surface normal. Surface normals is like, especially for vase, I realize this thing is totally rotational symmetric. Right? So you have a pretty explicit knowledge, a parameterization that you can use. That is, okay, if the thing is rotational symmetric, maybe I can model it that way. Right, so you have a bit of explicit knowledge about the geometry of the object as well as for the material of the object, because I think it's relatively safe to assume that this thing is homogeneous in the sense that every point on the object is reflecting light in the same way. Right? So every point on the object can share the same parameterization. That is, okay, let's say the parameters in this BRDF reflectance function. So you have explicit knowledge about its surface normals and materials. And there are some other, more subtle knowledge or inductive bias that you may want to leverage. For example, if you look at albedo, then we realize, it's not like this thing is pure color, right? So it's not like, oh, I can model every pixel. I can enforce that every pixel on the albedo maps has to have the same color. But this thing does look like, perceptually similar to me, right? Here and there, every point, every patch or every region on the texture of the object should look kind of pretty similar to me. So I have this kind of implicit, similarity or perceptual similarity bias, which is hard to write down as explicit mathematical equations, but it does give me, some kind of information about what the albedo map should look like. So I'll say this is like implicit inductive bias. And there are knowledge that priors that we have on the intrinsics we care about. And as we said, we may want to think about how we can leverage these biases or structures for object understanding and decomposition, this inferring process. So we're inspired by this earlier work by Elliot Wu, who back then was a PhD student at Cambridge. And he did this paper, which won CVPR Best Paper Award. CVPR is like the top conference in computer vision. And also in computer science, people care about conferences. So conference is like the top journal. Think about it that way. Although it published many more papers than math journals. What he did in this paper is you have an input image of a face, and then you want to infer the 3D geometry of the face and albedos as well. What he observed is there's this underlying causal structure, right? The modeling process, right? What makes the image look the way it is? That is, it has there's camera viewpoint, there's lighting, there's the underlying depth and albedo, like the texture of the face, and you can use that to reconstruct it, just like what we had before. Doing this kind of reconstruction. But this thing is really under constraint, right? Think about it. You have this. Think about it as you have the output, which is like input image is the I, is the whatever, but then whatever the I, but then it's a factor. It is a function of all these things for A, B, C, D, right? So you have a function of a bunch of different things, and then let's assume that A times B times C equals the output, which is I. But then now you're given I, and you want to infer A, B, C, right? That's really hard. It's under constraint. There are infinite possibilities. So how can we resolve that constraint? And what he observed in this paper is, okay, for faces, it is mostly symmetric, reflection symmetric. But what is really symmetric about a face is not like, if you look at everything here, then there's no reason to assume the lighting, for example, is symmetric. Right? So what is really symmetric is the intrinsic of the face. That is what really belongs to the face, which is the depth and albedo. Right? So the shape and the color of the face should be mostly symmetric. So if you have that knowledge, then what you can do is you can do a horizontal flip of the depth and the albedo maps. And you realize that, okay, if I rendered image in the original inferred output, or if I flip the depth and or albedo maps, the reconstruction should still look the same. So once you have that additional prior, you can use it, you can enforce it in this way. That kind of small idea, small trick turned out to work really well, that you can train a collection of faces without annotation. And during testing, just giving a single image of a face, you can turn that into 3D and see it from different views and re-render it. And nowadays, I think there are a lot more methods with all these different ideas in computer vision and deep learning that can help you solve this problem even much better and faster. But I thought this is still kind of cute. And also, it's really unsupervised, which is very unusual because most of these, the fancy demos you may have seen from the internet, a lot of them, they're really supervised, heavily supervised. So if the thing is unsupervised, I think it has a lot of potential in scaling up to wild videos. Okay, so Aya was a PhD student back then, and then he came. I was spending some time at Google, and then he came as a intern, research intern. So we thought, okay, is it possible for us to extend this work so that we're not only just using Symmetry for shape recovery, but then we can leverage more diverse inductive biases or the structures for image de-rendering, not just getting the shape, but getting everything else you care about. Right? So if we can do that, if we can de-render input image into all these intrinsic images, then you will be able to render from different views, like novel view synthesis, and you will be able to rely the objects under different lighting conditions because you also model the materials. Okay. So how can we do that? Especially as we said, we have pretty explicit priors about surface normals and materials, and we have some more implicit priors about albedos. So how can we enforce that? Especially now, of course, you want to use this kind of end-to-end neural network. So what we did is it's a little bit rather complicated, but turned out if you extend it, turned out to be pretty simple. So you have an input image, and because you have this explicit priors about the shape, right? You can have specific parameterization, the solid revolution parameterization on the object shape, so that you can parameterize the object as a single scalar, which is the height, and a vector, which is the radius at different heights, right? So you can have this parameterization as a way of enforcing your prior knowledge about object geometry, and you can also, of course, estimate the pulse. And then once you can do that, we can re-render the objects in computed silhouette. You can compare the silhouette with the silhouette of the object from the input image. That's our first loss. And once you have the shape, you can unwrap the object so that you can actually get the unwrapped surface normal maps and texture maps. And you can do this relatively standard, I would say, intrinsic image decomposition thing. That is, you can have the surface normals and texture maps. You can estimate the environment maps and the materials of the objects, as well as you can estimate diffuse albedo maps. And once you have that, you can put it back with, once you have lighting materials, you can put the camera pulse in shape so that you can compute the diffuse and specular components, and then you can put albedo back so you have the reconstructed texture maps. And finally, you can rewrap the objects so that you can go from this unwrapped texture map back to the original input image space, and you can compare your reconstructed image with the original image. So that's the second loss. Here, realize that, for example, for materials, right? You're enforcing the constraint that is the object is homogeneous. That is, every point on the object is reflecting light in the same way. Right? So here, by assuming every point has the same parameterization for the materials, you're sort of implicitly enforcing the constraint of the prior knowledge you have. That is, the object is kind of homogeneous. And finally, right? The hardest part is always this albedo map, right? Because what's the actual color, underlying color of the object, right? This problem is really hard because especially if you look at the input image, you realize for the kind of shiny objects, right? They have these kind of specular components in the sense that the thing is like really overexposed. If you look at, if you're a computer program and you read this picture, and you look at this pixel, the pixel value of this pixel is this region is probably like 255, right? Which is pure white, right? Because the thing is overexposed. Human eyes are great because we sort of realize, oh, this is a specular region, and the underlying color of the object might be also like green, red, sorry, not green, red, orangish. But for computers, how can you tell from this 255 overexposed pixel that the underlying true color of the object is totally different? So as we said, we have a little bit of implicit priors about the albedo map. That is, it should look perceptually similar to us everywhere. So what that means, if you want to translate it into neural network implementations, then one is, okay, if it looks similar everywhere, then what if I just compute a mean, and then I use this mean albedo, put it back with the rendering process, I can get a mean albedo texture, and I can rewrap it so that I can compare this reconstruction but only with mean albedo, and then compute the difference between that and the input image. So that's your quick way of enforcing it. That is, okay, if it looks perceptually similar here and there, if I average them, it should look pretty similar too. more importantly, I have this additional prior that is, if the region looks similar, if the albedo map looks similar to humans everywhere at different regions, then that means, if I sample patches from this albedo maps, right, no matter if I sample it from highly specular region or if I sample it from non-specular region, it should look kind of similar to humans, right? Because this patch and that patch, if you look at albedo maps, they should really look similar to humans. The fact that they should look similar to humans means they should also look similar, ideally, to a machine as well. So what we can do is we can randomly sample patches from this albedo maps from highly specular or non-specular region. And I can send it to another neural network, right? So this is a pretty popular idea back then, the kind of generative adversarial network idea, right? So you have this discriminator whose goal is trying to take patches from the albedo map and to tell, whether it's coming from a highly specular region or from a non-specular region. And our goal is to produce a albedo map so that you can sample up patches from it, from no matter a highly specular or non-specular region, and the patches will look similar enough to the discriminator, which will not be able to tell which patch is it coming from. So specifically, right, so I have a particular albedo maps, I can sample patches from it, and some of them may come from non-specular regions, some of them may come from highly specular regions, and send them to a discriminator, and discriminator whose goal is to classify whether it is from a non-specular region or highly specular region. But if my predicted albedo map is consistent enough to humans that look perceptually similar everywhere, it should also look perceptually similar everywhere to the machines, and whose discriminator, this discriminator should not be able to tell if the patches are from a highly specular region or non-specular region. This is kind of a simple idea, and when you realize it, it's like purely, as part of a neural network, everything is end-to-end trainable and differentiable. But it is, I thought kind of smart ways of enforcing or incorporating the biases we have about different parts of the intrinsic images, and also contribute very importantly to the success of the algorithm, which turned out to be working pretty well, right? Doing testing, as we said, just give me a single image, you can de-render it into all these things you care about, the intrinsics you care about, geometry, textures, materials, and you can, turn an image into 3D, doing testing just from a single image. You can turn it into 3D, and you can, see it from different viewpoints, and then you can also relight it. This is just looking from a single image, but maybe you're totally right that because you're just from a single. Yes. Okay. I think you're totally right that it is just from a single image. We're not directly doing any kind of image completion, but it's true that the field of view of the object is like you can't really see 360 from the input image. So what is basically happening here, as maybe I'll show this following example, is this is the input and this is the output, right? So that's basically what's going on. But then to produce this demo, what we did is you turn it into 3D, but then you only see like 1/3 of the image, so you just copy the texture. Yeah, you're just copying the textures. Yeah, so you just leverage the fact that it's rotational symmetric, you just copy textures a few times. The geometry you're assuming it is rotational symmetric, right? So you only estimate, exactly. Yeah, you can also turn in some include like paintings from a single image into 3D, render from different views and relight them. Okay, this is pretty cool, and I feel like it works pretty well. But if you think about AI system, then people are like, okay, AI system should be very general. But if you look at our examples, I thought it's still pretty cool, and it's general enough that it works well with everything that is kind of rotational symmetric. But unfortunately, the world is not made all of exclusively of rotational symmetric objects. There's so many. It's not like we live in a world of just cups, but there are a lot of objects. Actually, a surprising number of them are rotational symmetric. If you look at this table, there are talks and everything. But okay, there are also a lot of them that are not rotational symmetric. So when we present, there's so many of them. Okay, when we present a work, I think a common criticism is, okay, then how can you scale generalized beyond objects that are not rotationally symmetric, which is, I think, a valid criticism. so so we just think about what is really missing and what is preventing us from generalization. And so I think the underlying question is, here you're assuming an object geometry have this particular parameterization, right, which is sort of resolution parameterization. And in the natural world, if you look at the objects, a collection of objects, the fact that they're sharing something, they're sharing. It's not like every object or every category or every, if I say chairs, it's not like every chair share the same geometry representation. So what is really shared among a number of objects? And this motivates us to move on to this following work, which now has been out for like a year or so. I still really like it. That is, if you look at this bouquet of 100 roses, and you realize they're all roses, right? They're kind of very similar, realized. And, they have something that must be shared, right? There's a reason that we call them a rose, right? When you say the word rose, it refers to something. There must exist something, right? Some underlying properties that makes an object a rose or not a rose. But that property is not for roses being rotational symmetric because they're not rotational symmetric, right? So what is really special about them, or if you look at all these instances of the roses, right, what really is the underlying shared assumptions between these instances? And we realize, if you think deeply about it, then they're just examples or instances from the same object category. Think about it, you have this underlying distribution of object intrinsics, the geometry, texture, stuff like that. And you're just sampling from them, right? So all the instances you get here, they're just samples from that kind of underlying distribution. So what is really shared between these roses, it's not a particular parameterization on the geometry or texture. It is the fact that they share the same distribution of object geometry and textures and materials themselves, right? So the fact that what they're really sharing is not a specific parameterization, but this general distribution. And maybe there are some objects that have a more specific parameterization on distribution, but more generally, the fact that they're sharing the distribution is important. And so if you can really model that distribution, then what you will be able to do is you will be able to sample from the distribution so that you can think about the example I showed at the very beginning, right? Yeah, this distribution of the geometry, textures, materials. And if you can really leverage the fact that they share the same distribution, you can use that in your inference systems. Once you can do that, you can, again, during testing, sample from the distribution, and you can get objects from with different geometry, with different textures, and you can, of course, render them from different views and different lighting conditions. So that's kind of the main idea, which is kind of a bit conceptual. And so in this work, we actually did that, right? So what we want to do is we want to leverage the fact that these objects are different instances and share the same distribution of intrinsics. You no longer assume you have specific parameterizations on the intrinsics. You no longer assume the geometry has to be rotationally symmetric. But what you do assume is they share that same distribution. So we learned a general model that can go from a noise factor to a distribution you can sample it. So this is a general model in the sense that you can sample this noise factor, you'll get different instances of object geometries and albedos. You can put it back with other things like environment extrinsics, like lightings and pulses, and which allows you to go in this forward rendering direction. You can compute the shading of objects. You can put back albedo, so you have the appearance of the objects. You can put back camera parameters, so you can render a picture of a fake rose. And you can compare that with images from, examples from the single image, and there's a real rose, right? There are a bunch of real roses. And then now the goal is, instead of just saying, oh, albedo maps have to look similar here and there, you're like, the underlying modeling of the distribution of object intrinsics should be accurate enough so that when you put it back into this forward rendering loop, right, the produced output, the rendered pictures, the generated fake roses should look very similar to real roses in the sense that machines cannot tell, right? So you can have a discriminator that tries to classify whether input is a real rose or a fake rose. You should not be able to tell if you have learned very good generative models about these intrinsics. Okay. So this is published was last year. So when we were doing the work, it was like a year and a half ago, and or even actually maybe more like 2 years ago. So back then, they don't have that many like diffusion priors and stuff like that, and we were still using this kind of a bit outdated framework nowadays, like this discriminator framework. But so which means if you can replace that with more like diffusion priors, you probably will get better results. And also in this work, we really want to explore how much you can get from a single image, right? So if you just have everything is just learning from the single image, just like before, doing testing, but also in this particular work, we have a new assumption that is even during training, you're gonna have this only one single image. So you don't have any pre-training, you're not leveraging image data sets. You just want to do self-supervised learning on this single image, which does give you a bunch of instances though. But still, all the training and testing is just done from this single image. And you're also not using like a diffusion prior, which has been trained on millions of images before. So the result here is, I think, it's kind of a bit suboptimal. But I thought it's kind of a pretty interesting intellectual exploration. So more on the results, right? So you just get a single image with some masks on where the roses are, and you want to learn to infer the distribution of object intrinsics, which can allow you to then render at the bottom, which is the roses from different viewpoints. At the second row to bottom is the roses under different lighting conditions, and in the middle row is because you're learning a distribution of object intrinsics. You can sample from them, so you can generate roses with different geometries and stuff. The variations here is also a bit limited, just because you're learning everything just from a single image, right? So you want to capture, so the variation, the distribution you can capture is basically, okay, how these roses are like. So it is a bit limited, but I thought from a single image, try to get as much as possible by leveraging the physical priors you have about a physical world. Right, so, yeah, so this is done by my PhD student Yingzhi. The geometry distribution learned from just, sorry, say it again. Yeah, from actually less than 100, but yes. 50. Okay, so here are some more results. Everything here is trained on one single image and directly sample from it. So you can do similar things. You can see things from different views. You can render in the different lighting conditions. You can have different samples about its possible geometry. Okay. How many time do you have? 30 minutes now. So I think I want to try to wrap up in like 15 or 20 minutes. Yeah. So that 27. Yeah, but it's better to stop early and take some questions. Yeah, I'll try to wrap up in 20 minutes. Okay. So this is about single image. How much you get from single image about object, increases, and we can go a little bit more than that, right? So in particular, maybe I spend a little bit of time on the form, which is think about it as the hierarchical structure, right? So if you look at a lion like a human, you realize it's not like humans are rigid body, right? So humans are articulated rigid bodies in the sense that you have degrees of freedom to move, lions can move and stuff like that. And objects, even if you look at objects, objects have parts, and maybe you can separate object parts and you can get different components of object. So is it possible for us to go a little bit beyond that? So you can, in particular, I think I'm going to talk a little bit about like articulation of object geometry, right? So in the sense that you have a lion or you have a bunch of horses, is it possible for you to infer all these things you care about, but also getting the skeletons and articulations of objects? And so this goes to our most recent work, in the sense that you are, in particular, I think we're trying to think about the roles example as what is really shared is for a single object category is the underlying distribution of their geometry and texture. But there are things that are shared not within a single object category, but across object categories. Right? So in particular, in this work we talk about, we try to learn the underlying articulation, but that is sort of shared among a bunch of animals. And here the assumption is all animals are like quadrupeds. So they have 4 legs. Okay. So we're not trying to study fish or snake or anything, but we try to model all the quadrupeds of the in the sense that you can learn distribution, you want to infer, you can sample from the distribution, but you can also try to do single image reconstruction. In the sense of taking an image of a quadruped, you can infer its textures, geometries, and things we care about, but also at the same time infer the articulation of the objects. What is happening here is similarly you train on a bunch of internet images without annotations. Again, nothing here is really annotated, so you just have a bunch of images which you can Google search or you can use existing object data sets. Have a bunch of images of these animals, and because now you're dealing with a number of object categories, not just a single object category, so we sort of assume there is a kind of a shape bank, which is a collection of base shapes, which defines think about them as the basis, and they're the subspace they support is the possible deformations of the quadrupeds you care about. And on top of that, you're also doing instance level predictions, right? So instance level predictions include, what's the possible deformation, which is basically think about it as the I would say coefficients, right? So how the weights of these bases, how are they combined to explain the deformations you observe on this specific instance, the articulations, as well as the things we just talked about, albedos and lighting viewpoints, right? So on top of that, you have a bunch of self-supervised reconstruction losses, just as before. One is this pixel level photometric loss. There's the silhouette, which is more on enforcing the geometry and help you learn deformations. But also nowadays, this is like recent work. So we have incorporated some new advances in deep learning in the sense that there's this thing called very powerful recognition. Now nowadays they have these kind of very large scale vision language models, or people sometimes call it foundation models, right? So if you play with GPT-4, all these GPT-4 systems, they can take an image and sort of explain what is there. But a bunch of them, they're like these vision models. They learn very good features about the input image, especially the semantics of the input image, like what is the category of the object, what's the part of the object, and stuff like that. So you can learn using these kind of features extracted from the pre-trained large-scale neural network. In this particular case, I think we use this pretty standard thing that now everyone more or less use, called the Dino V2 features. Dino is this some open source neural network released by Facebook, which allows you to better capture the semantics and enforce the consistencies in your reconstruction. But what is most important is, it is doing category agnostic training without category labels, right? You train a bunch of images of the quadrupeds. You do know they're all quadrupeds, but you're not having annotations on the geometries of objects or textures of objects. Before, you're also not assuming annotations on the semantic label. It's not like, oh, this is a rabbit and that is a horse, or that is a dog. You just assume, just have a collection of images, and you want to learn these intrinsics, and on top of it, the articulation, the deformations of the objects. So here are some more results, and doing testing is similar. Going from a single image, you can turn it into a 3D. You can see it from different viewpoints. You can rely them. But now, because you have articulation, you can sort of play with them and see the possible deformations of the object. But here, we're not learning like the motion basis, in the sense that everything here is like manually created. As you see, we're basically not learning how objects can move. So there's no point in arguing whether the motion is realistic or not, because that's not our goal. Here we're just saying, if you have the articulation, then you will be able to play with the object and see how they may deform. So that's the case for, I would say, natural objects like animals, but there are also a lot of forms in man-made objects, artificial objects. There's even more structures, right? If you look at, come to this place and be an MSA, you have all these beautiful buildings. And the buildings look nice because they share some particular, I would say, regularities or architecture designs. And that's the case for, for the tables, for the chairs. You can see a lot of repetitions and symmetry in these man-made objects and in scenes like buildings as well. So that's another form of intrinsics, although the intrinsics here no longer come from nature. Everything before we talked about, they more or less the intrinsics come from nature. But here we have some kind of additional forms like repetitions and symmetry, which are, actually the base example is not true from nature too, right? The base example is also a man-made objects. So you have some kind of priors or intrinsics that are, especially on the form level, they're sort of introduced by humans. And especially about when you look at forms, right? A lot of them come from humans. So is it possible for us to also leverage those kind of priors in better modeling the repetition and hierarchies of the objects? So what we did is we also applied similar ideas that we want to go from image or sometimes like raw shape, like just raw geometry, to infer what's the underlying structures, of like the form of the objects. And in this example, in this kind of a bit earlier work, what we did is you take a shape and you want to capture like leveraging these kind of program-like representations like for loops and stuff like that to capture not only the specific geometries of objects, but also the regularities like the repetitions and symmetries of objects in the case of a programs. So I think procedural modeling has kind of a long history in computer graphics, right? There are all these kind of past successes, and here we're sort of trying to do a little bit of that, but more on the inference side, right? So going from image, is it possible for us to have like a program-like representation to explain the input? And I think the same theme we talked about, it still all applies, right? So if you look at geometry and texture, you realize, okay, there's no data, right? So if you look at internet videos of lion, then there's just no underlying geometry or texture annotations of the lions from the videos. And that's the same case here for the programs, right? So if you look at shapes, first, shape, you don't have that many shape data anyway. But even if you look at existing shape data, including the most recent ones, like Observerse or something, right? There's still no annotations on the programs of the underlying objects. Right? So where can you get all those annotations? And we still have a similar idea. That is, we have this, more like analysis of a synthesis reconstruction-based approach. In the sense that you have a neural network that try to infer the program from the input. We also have another neural network that try to execute the program, that try to run the program so that you can produce the output from the program. You can do this kind of training in a more like supervised way. There are some more nuances here, including how you design a program and how you can actually get the training started, which is pretty subtle. So I'm going to skip all the details. But you still have the similar ideas about using self-supervised learning to get intrinsics, although here the intrinsics is more like introduced by humans at a regularity and repetition level, about the form of the objects. And more recently, we have some more results now. If you look at earlier work, then you realize, okay, the shapes, the regularities was captured, but what was not captured is here you're assuming all the entry-level primitives are just like simple geometric primitives like cuboid or cylinder. Right? So just like the world is not made of revolutionary objects, and the chairs and tables are not just made of cuboids and cylinders. So we have extended our work so that the primitive level, part level, the object parts and the leaf nodes, right, in the programs, they are no longer assumed to be simple geometric primitives, but instead they can also be like learned neural networks. Right? You have a learned neural network parameterization, like these days people call it like implicit function. And it's like an implicit neural network that captures the specific details of the object parts, and you have a higher level program that captures the structures irregularities. Right? So look at the case of airplane. Then here you can use a program to sort of enforce that the left wing and the right wing of the airplane should be exactly the same, right? So that's the only thing that differs. What's the difference between these two wings is the extrinsics. Right? Think about it. It has to be reflectional symmetric, right? The thing has to have the same shape, but the only difference is think about it as their poles. And the representation here sort of enforces that by saying, okay, you have these extrinsics that are explicitly modeled in the program, but you have the intrinsics, which is geometry and stuff like that, which is learned by neural networks. So they have both this kind of I would say, reconstruction accuracy as well as the high-level regularities that you care about. And we did a little bit of that to C's as well, in the sense that, okay, you have like a building and you realize, okay, the building looks nice, but what if I want to interact with it? Let's say I want to go from this picture and then I can, I put this into Adobe Photoshop GUI, but the underlying algorithm is actually ours, in the sense that you first, use the pretty standard segmentation to get these segments. And then after that, you want to interact with it in the sense that user can just have a single drag, and then the building will just be made taller. You can also, make the building wider and stuff like that. Now, to solve this problem, it requires you to have understanding at multiple levels of abstractions about the image. So at the lowest level, you are like, oh, the object has particular texture, so I want to keep the texture. At the middle level, you're like, oh, the object has different faces, and every face has its own surface normal, its orientations. I want to keep that orientation. I have to understand. I have to make sure that the edited images still respect perspective projection. Right? And the highest level, you understand that okay, they're like floors, and the windows are repeating themselves. And if I make the building taller, you actually have more floors, and the windows should still continue to repeat themselves. So similarly, this requires you to have modeling object intrinsics not only about the geometry and textures, but also about the forms and regularities, which is sort of like a strength of this kind of hybrid, say neuro-symbolic, you can argue. The program-like representation in the sense that you have the symbolic components like programs or repetitions, which are explicitly written, but executed by neural network though. Well, you also have these neural components, which is like the geometry and the textures. How can you parameterize that? Which is very hard to parameterize. So you parameterize them with neural networks. It allows you to do different things like view synthesis in the sense that you can go from a single image and you realize, okay, there are a lot of lights that are kind of repeating themselves, right? It's kind of similar to the building example, but now you're inside the building in the sense that, okay, now I ask you, what will happen if I turn around? What are you expecting to see? Of course, I don't know, but if I have to make a guess, I would say, yeah, maybe you can extend this corridor if you turn it around into an infinite corridor, right? You still expect all the lights to repeat themselves. You expect all the, kind of the cast shadows and everything should look realistic. So all this, again, doing testing, you just need a single image, right? You try to infer the textures, geometries, but also the underlying form or program of the scenes. Allows you to do rendering. And again, this is 2020. Back then it was kind of cool, but then now people are like, here you still assume things are like repeating themselves regularly, and the natural image or the natural world is very messy, right? There's no reason to assume if I give you input image, things have to repeat themselves, or you're seeing the input image, you're seeing objects from like a particular direction, right? So what if the objects are not repeating themselves that well? How can you deal with that? How can you generalize to more complex things? Similar criticisms. So we have did some extension to the work in the sense that now we can take an image, which doesn't have to be a image with repeated objects like these kind of lights or the floors, but you can still do 360 now obviously as this. So what's the difference between these two, right? So this work on left I've been spending my entire talk talking about, right? Okay, how you can have these inductive biases and intermediate representations, how you can take knowledge from computer graphics into this rendering process or modeling process, make it differentiable so it can be integrated with the inference neural network. And doing testing, you can go from a single image to all the things you care about. You can use these for different applications like novel synthesis, relighting, and stuff like that. On the right, more recently, we have been exploring a slightly different approach, which is, before I've been saying, yes, everything I talked about before has been, you have physical object intrinsic sensing intermediate representations, and you can de-render, you can re-render it, you can have the reconstruction loss. It does have some assumptions, right? In particular, it sort of assumes you have a graphics engine, and graphics engine has to, reconstruct the world pretty well, which is not often the case. There are a lot of things that you can't really model that well, and the graphics engine has to be very fast because you're putting it into a training loop, and so you have to do like feed-forward propagation and backward propagation, and to use the reconstruction loss to backpropagate and edit, and train a neural network so that you can have better isolation of the intrinsics. And sometimes the neural networks, they may be good, but they're very slow. Right? They may be, there are a few issues. Right? First is there are a lot of things that we don't know how to model. Second is for things we know how to model, sometimes the model itself is not differentiable. And the third is sometimes the model itself can be made differentiable, but it's really slow, right? So if I have any of these issues, then the whole pipeline won't apply. And unfortunately, that's like most cases in the world. So the different paradigm we've been exploring more recently, which I'm not sure if it's better, but I think it's a different idea. It's related, and we can see eventually how we can integrate them. Is instead of having physical object intrinsics as intermediate representations, what if we trying to distill them from a large pre-trained neural network, right? So if you have a large neural network that has learned, let's say, in a self-supervised way for video prediction or for whatever things, you're sort of implicitly doing like an encoding, decoding process, right? You have think about it as a large autoencoder, or you can think about all these like diffusion models in these days. They're sort of doing that, right? Like the diffusion transformer, whatever. You're having this large pre-trained neural network that is already doing reconstruction objective, trying to fulfill that objective. But now they must have learned some information about the object intrinsics you care about. So instead of putting intrinsic and intermediate representations into these large neural networks, what if you first train neural networks and try to distill as much as possible of these intrinsics from that neural network, right? So that's the motivation behind our more recent work on algorithm synthesis, in the sense that you have a large pre-trained diffusion models, and you want to distill the 3D geometry of the input scenes from the diffusion models. And the specifics about that, I don't have time to talk about, but happy to talk about it offline. So the benefit of that is it's much more general, right? So now during testing, you can take any, no, it's not really any. It's still bounded to your data sets. But arguably, it's more or less like any, all these different pictures. And you can turn a single image into 360. And there are also a bunch of other challenges, so which I feel like it's not obvious that this new paradigm is better than old one. I think they each have their own strengths, and going forward, what's the best thing to do? It's not that obvious, but at least for the new paradigm, it has some benefits. For example, it's general, as we were saying, and I think there's kind of you can sort of, at least I think in the shorter term, also expect the models to get a little better, just because we're sort of distilling from these pre-trained image diffusion models, and in the future, and we're starting to have some of these video diffusion models like Sora, and we can sort of expect these video diffusion models to get a little better, or even in the next few years, because there's so much video data that hasn't been used, hasn't been modeled that well. So if we model them better, you can expect the video diffusion model to get better. So there's still more to do in the distillation approach as well. And finally, we have this most recent work that my student Coben. By the way, this was done by Kyle, who was my student as well. And there's another my student Coben, who thought about, is it possible for us to not just distill from a video diffusion model to get object geometry and radiance so that you can render from different views, but what if I also distill from a vision language model, in the sense that I can not only think about going from a single image to 360 scenes about what should be there in the scene, but also expand the scene. That is, okay, if I'm in a bedroom, if I want to move around, what do I expect to see? Because language model sort of knows, okay, what should be in the bedroom, what should be next to a bedroom. So what he did is you can use a large language model to generate a long range of scene descriptions. And you can put that together, with some scene generation models that produce the images corresponding to the scenes you care about. You can back project into 3D. You can do, use pre-trained models for outpainting, and you can sort of repeat the process. And also, you can use this language model to verify whether a generated scene is realistic or not. So use it as a generator, but also as a critic to verify the generation. Eventually, what you can do is you can sort of go from a single image, again, similar to any image. So that's what we call it from anywhere, in the sense that you can take any image. You can not only see a 360 of that particular scene, you can actually create like a kind of a journey, in the sense that you can, going from a scene, navigating, going from an image and navigating the 3D scenes. And because, again, this is also a generative process, you can go from the same scene and produce different journeys. So that's what we mean by to everywhere. You can go from anywhere and to everywhere. This is image condition. You can also do language condition. I think we're also putting some kind of a Chinese poems, which are nice because Chinese poems are, it's vague. I think because they're vague, right? It's like 黄河入海流. It's very vague, right? So you can generate something that looks pretty good, right? Because it's vague. Anything you generate is kind of pretty. They all look pretty reasonable. Okay. Okay. So that's all I want to talk about. And there's motion, but unfortunately for motion, we don't have very good results yet. So I prefer not to talk about things if we don't have good results. So let's wait until next time. To summarize, we have sort of explored the idea of understanding visual world through object intrinsics, and I think the fundamental question here in building our perception system or scene understanding system or any type of AI system is the same. That is, they have this underlying fundamental question on learning versus modeling. Right? So what's the minimal assumptions? In a particular case for 3D perception, for 3D scene understanding, what's the minimal assumptions, right? So, because every time you're building something and people are like, oh, you know what, that may not be generalizable, or there's this kind of at this moment, there's this kind of pretty famous article called The Bitter Lesson, in the sense that people always argue, oh, if you're putting something, then eventually it's going to be outperformed by data. So it's just going to want to have more data instead of having more representations. Right? That is, in many cases, that could be true, but I think it's also tied to the fact that people haven't thought too much about what's the right assumptions to put in. Right? It's not like you want to put in as much as possible. That's probably not right. It's also not the case that you want to put in as minimal as possible, because fundamentally there's no way of putting nothing. You have to put in something, even if you're just putting like spatial convolution or self-attention as in transformer. Right? So convolution neural networks and transformers, they already have some assumptions. So then what's the right level of assumptions and the minimal assumptions that we need to put in? And I would say, maybe a large part of it is sort of like what we're thinking about here, in the sense that what are the physical object intrinsics, or so why they are the right inductive biases? Because here we're doing inverse rendering based on the causal structure, and it's physical and it's universal in the sense that they're from graphics, but graphics is trying to replicate a physical world, right? So fundamentally they're from the physical world, and you're not like coming up with things yourself. It's like, oh, I drink some coffee, it's have a new idea. It is really like you're trying to understand how the world is organized, and you take these knowledge rules you learn from the world in the sense that this is, every picture you have seen, they are produced by, there's light transport, there's perspective projection, there's object has geometry and texture, right? So it's kind of universal because it applies to every image and everything you see. It also captures the underlying physical and causal process that produce these pictures. So when you make those kind of assumptions, of course, there are a lot of like implementation challenges, such as the graphics engines are not good enough or fast enough, as we talked about. But these inductive biases are general and universal, and therefore there's no reason to assume they won't generalize, because there really is the thing that is shared across every visual observations. So they should be able to be generalizable, although specifically, what are the domains and what kind of differential renders or neural renders you want to use. There are a lot of like specifics to be figured out. So yeah, if we can do that, then as we said, it allows you to effectively use in the wild data, large-scale internet data without supervision. It can do, also help you to potentially guide you on how you can generate synthetic data, how you can produce synthetic data for training, and it provides natural interpretability and controllability in the sense that you can, as we have shown, render objects in different views, or change lighting, change geometry, change articulation, stuff like that. And as we said, it should help your generalization and leverage, especially by providing composition. Thank you.
Okay, so time for questions.
Yes.
What space?
Oh, distribution. What is that? What is that representation, right? It's a neural scientism function. It's a neural network approximated SDF, neural SDF.
So what's your input? You generate a shape from the neural network, right?
The input is random noise, and the neural network take a random noise and translate it into.
So what's the dimension or the size of the neural network? How do you determine that?
Oh, what's the size of? Are you saying what's the size of the? What's the size of the neural network?
Yeah.
Basically, it's the largest possible that we can fit into the GPU memory we have back then. Yeah.
Even for 50 roses, you have.
Yeah, that's right. Yeah.
Hi. I think it's very inspiring work, and we see that the video generation models like Sora can generate very like realistic views, but we actually want to make it more like controllable, because now by only prompts, the video generated can still be fake from some perspective. So do your work like the rendering things could be maybe integrated with the large video generation model?
Yeah, exactly, right? So that's what I'm saying at the end, right? Because if you look at, for example, this work, right? So it's trying to distill from image diffusion models, right? And how much you can get from image diffusion models about how the scene will look like from different viewpoints and underlying shape. I think video generation models, they're supposed to be able to capture better, I would say, object motions and how the objects should move. So maybe you can argue a bit more 3D as well. They don't have perfect 3D consistency, but at least they should have some knowledge about 3D. In practice, we also try that. It didn't work that well for a few reasons. First is we don't have access to Sora, which seems to be much better than the other video diffusion models, or at least much better than anything that is open source. The open source ones are horrible. So you can do very little with them. So it could be the case that for people who have access to Sora, or maybe the other competitors, I think these days there are some pretty good ones from China as well. Like Kuaishou has this new model called Kelin. I think it's pretty good. But anyway, there are a few things that seems good. So one is if you have access to these better models, maybe it'll work better. But second is I think there's also some fundamental challenges in the distillation approach. That's why I was saying, it's not obvious to me that this first style, the first approach, this I was inductive biasing the loop approach, is not going to be compete as well as this inductive. I was structure in, and this is structure out. it's not obvious that structure L would be better. Although, yes, right now we focus a lot on structure L and how much we distill from image diffusion or video diffusion models. But the first challenge is, yeah, we don't have the best access to best diffusion models. So it doesn't work that well. The second challenge, which is more fundamental, and maybe will make this style approach, it's not going to be eventually the one that really outperform the first one, is I think all these diffusion models have this challenge that is, for generative modeling, you just have to get something right. You just have to have, if I have, as I said, if I give you a point, or why is it easy, right? Why is it generative modeling easy? It's like, there's this famous Chinese proverb, right? Back then, people say, what's the easiest thing to draw? The easiest thing to draw is to draw a ghost because no one has seen a ghost. So you draw anything, that's great, right? So if you look at all these demos of video diffusion models, it's similar in the sense that they have this prompt, and the prompt is very vague. A woman walking on the Tokyo street at night. This is very vague, and in the sense that, if you look at all the possible distribution of images and videos, then there are infinite many possibilities. And all you need to do is you just have to capture one peak really well. You just have to capture one mode. It just looks beautiful. And it's great, right? Because it looks so well. It looks so nice. And people are like, oh, well, they have solved the problem. But they have not solved the problem. All they have solved is they capturing this one particular mode really well. So now if you want to use them for distillation, you have this big problem, right? Because unless your input image is exactly that mode, then you can perfectly distill it. But if your input image is, provably is out of distribution, right? It's like, it's not the things that they capture that well. Then when you're trying to do distillation, you don't really get the precision and the fidelity you want in terms of, let's say, the shape of the objects and stuff like that, because that's the thing that the generative model cannot model that well. It was modeling that particular peak very well, but unfortunately, your input is most likely not that peak. So I think that's kind of a more fundamental challenge, and that's sort of have seen a little bit, right? Even with all these very good Sora image generation, video generation models, it is very hard to put camera control into it. It's hard to make them to be conditioned on camera parameters. So how much can we get from generation models? Are they going to are this kind of distillation-based approach going to fully solve the problem? I think there's a lot of uncertainty. But of course, there's also a lot of challenges in this kind of structure in the loop approach as well. So it's not obvious, I think, how we can really, what's the best solution, how we should move forward. Maybe some combination.
Okay, thank you.
More questions? So, okay, let's thank Professor Wu again.
Thank you.